You connected two ends of different metals together and heated one junction with a candle. At first, you noticed nothing, but when you connected a multimeter, you were surprised to find that the circuit generated voltage. Moreover, the greater the temperature difference between the junctions, the higher the voltage produced. However, this phenomenon was discovered over 200 years ago by a man named Thomas Seebeck. At the time, he accidentally joined two ends of different metals and heated them with a candle, only to discover that a compass needle placed nearby rotated. This was caused by the electric current generated in the metal, which produced a magnetic field. Thus, this phenomenon was named after him as the Seebeck effect. A circuit made of two different metals is called a thermocouple. The Seebeck effect is also the fundamental principle behind nuclear batteries used in modern spacecraft. To better understand how nuclear batteries work, let's examine this process at the microscopic level. What exactly happens in a thermocouple? As we know, metals, as conductors, contain freely moving electrons. However, different metals have varying free electron densities. When different metals come into contact, a tiny voltage forms at the junction. But this voltage is insufficient to sustain a current in the conductor. Even if the metals are connected to form a closed circuit, no current will flow because the voltages at both ends cancel out, resulting in zero net voltage. However, when one end is heated, the energy and density of electrons in each metal increase, thereby raising the voltage. The equilibrium is disrupted. The net voltage across the junctions is no longer zero. This creates an electric current in the circuit. The magnitude of this voltage depends on the material's Seebeck coefficients and the temperature difference. Each metal has a specific Seebeck coefficient, and the voltage is calculated using the formula. Once this is understood, the principle behind nuclear batteries in spacecraft becomes straightforward. They consist of thermocouples made from two different conductive materials. Multiple such structures are connected in series to form a closed circuit. Thermal conductive materials are attached to both sides, creating a thermoelectric plate. Multiple plates are then arranged into a cylindrical structure. A radioactive heat source is placed at the core, creating a temperature gradient between the inner and outer surfaces. This generates an electric current. The full name of this nuclear battery is the radioisotope thermoelectric generator. The radioactive source in such batteries typically uses plutonium-238, a radioactive isotope. This isotope undergoes spontaneous decay, releasing alpha particles and generating substantial heat. Temperatures can reach up to 500 degrees Celsius. The outer surface, exposed to space, remains at around -270 degrees Celsius. This extreme temperature difference creates a voltage, producing an electric current to power external circuits. Since nuclear batteries have no moving parts, they are exceptionally stable and reliable. Their operational lifespan is remarkably long, due to plutonium-238's half-life of 87.7 years. For example, the earliest nuclear battery-powered spacecraft, Voyager 1, launched in 1977, uses plutonium-238 as its radioisotope heat source. After 48 years of operation, it has exited the solar system and continues to function to this day.